Yeah, so normally I keep making noises until people come, but I'm just going to do it because you know why? Because the audience is no longer the class. The audience is the World Wide Web. Those people depend on me more than you guys do.
He's a star now.
I'm a star, right? I have 150 subscribers. Now, in truth, 150,000 would be a good number, but 150 is nothing to be, not proud about. One thing I am proud about is everybody who subscribes, more or less. You see, there are some people who are real subscribers. They are interested in science. They subscribe to all sorts of science channels. When my subscribers let me see who they subscribe to, I am their only science person. They're subscribed to all sorts of internet craziness, but I'm their only science voice. So for you out there, I'm looking directly at the camera. For you out there, this is for you. Okay, but I have to leave early today. So as I've been saying, I've been not talking about the cosmic distance ladder, and I've been not talking about it for quite a while now, but I'm going to talk about it today. Iran, I'm leaving in 45 minutes. Yes. Okay. Just 2 minutes late. Yes. So the question though is, to me, is what I'm always answering this one question in this class, which is basically how big is space, how big is time, and not so much the answer which I can't answer, which is where did we come from, where are we going, stuff like that. I got to get my water. Oh, there it is. Okay. How big is space? How big is time? And I came up with an answer to how big is space that I really love this week. Okay, so here it is, because and it has to do with the cosmic distance ladder. I'm going to talk about the sun and the stars soon in this lecture, hopefully. But I thought it would be interesting to know how big the sun is. So, for one thing, the sun is pretty big, as you might have guessed, and that big. Now, in this picture over here, there's Jupiter, Saturn, Uranus, Neptune, and that little thing down there that's the Earth. Well, yeah, wow. So this is one of the best pictures I've ever seen that compares the Earth to the sun, right? And basically, space is big, and the distance between things and the sun and the rest of the universe is really big. But this is really big. So we got to start with really big and then move on to really, really big. But this is big. How big is the sun? This gives you some indication, but I have a better one than this. There's a difference. You've heard me say this before. There's a difference between the temperature of something and the heat of something. Something feels hot. You say, well, it's got temperature. Well, the two things are almost unrelated. You can have heat without temperature. You can have temperature without heat. The sun seems to be a bit of both, hot with a lot of temperature. But actually, what happens if I told you that the sun was temperature without heat? That would be a little startling, to say the least. Okay? But somebody did a back of the envelope calculation and came up with this unbelievable fact. The sun is making heat. Heat is energy. Energy is a form. If I throw this, that's energy. When it hits the ground, That's energy. When it stops rolling, that energy turned into the heat that I heated the ground up for. And that heat then warms the rest of the room and fills the room with that same heat. Heat never disappears. Heat is energy. Energy is what the sun does for a living to give us the light that keeps us alive, gives us the energy that we survive on. So the business of the sun is making heat. Okay? How much heat does it make to give us all the heat that we need? Well, it turns out it's made in the very center of the sun. And in the very center of the sun, which is about, let's say the last 25%, 75% on the way down, no heat is being made. But at the center of the sun, heat is being made, and you know it's being made through thermonuclear reactions. You know that. The fact that you know that, and it's common knowledge, is really cool because a long time ago, meaning 100 years ago, not a clue. They did not know this at all, had no idea why the sun was shining. But we'll get to that in a bit. Inside the sun, there are thermonuclear reactions that we all know, and we're converting matter into energy. We all know that too, thanks to Einstein and Eddington, who's the guy who figured it out even before they knew about thermonuclear reactions. And the heat is being produced, thermonuclear reactions, is being produced everywhere in the center of the sun at the rate of the following analogy. Let's say you took a couple of iguanas and you piled them on top of one another. Okay? How about you filled a box full of iguanas, okay? Stuffed them in tight, okay? And measured the amount of heat that's coming out of the box of iguanas from the food that they ate. So they're making heat. They ate, now they're warming up the box. They're cold-blooded animals, so they don't make much heat. So they're heating up the box. The rate at which they're heating up that box, that cubic foot of box, is the same rate at which the sun heats up a cubic foot of its own stuff in the center of the sun. The heat being produced by the sun is no faster than the heat being produced by iguanas. Difference is, center of the sun, a couple of million degrees, iguanas not so much. So you got heat, you don't got temperature. Isn't that amazing? I just think that's insane. Anybody want to ask a question about that? Or is it all clear? No? Is it clear?
Very clear.
Very clear. Okay. Now the sun is taking 600 million tons of matter and smashing it together to make energy every second. It's converting 2.5 million tons of matter into energy every second. 1 gram of matter, 1 gram of matter can produce 25 million kilowatts of energy. 25 million kilowatts of energy, enough to certainly power this city. 1 gram of matter can produce 20. See, matter converts into energy. Energy, kilowatt is not energy, it's power. It's energy divided by time. You have to multiply it by time to cancel the time at the bottom, so you get kilowatt hours. Kilowatt hours is energy. You get billed for kilowatt hours, not for kilowatts. You can have all the kilowatts you want, but if you don't burn it for any length of time, you don't get billed. So it's energy you get billed for. And the sun is producing 25 million kilowatt, can produce 25 million kilowatt hours with 1 gram of matter. And yet, it's producing it at the rate at which reptiles could produce heat. That's insane.
If the sun would be filled with reptiles, it would be saying.
If the sun was filled with reptiles, that is the point. If you replace the sun, okay, the interior of the sun, with a bunch of reptiles, okay, and made sure that it wasn't hot anymore, millions of degrees, but comfortable room temperature, okay, the sun would produce as much energy, heat, flowing out from the outside as it does today. That's right. So there's that's insane. Okay.
Excuse me.
Yes.
Is the energy produced by movement?
No. In fact, so Marion, you need to get on the web and pay attention to the part of the thing that you just missed, because I began the lecture at 12:30 because I'm leaving at 12:45 today. I mean 1:15 today. Is the energy produced by movement is a great question, because in the old days, meaning 100 years ago, before Einstein knew anything, before the people knew that Einstein knew everything, there was the question of, well, how does the Earth produce, how does the sun make energy? And the answer was through movement. Simple. If you have something that's moving and it's stopped, like, for example, you have a car and you happen to be aiming it at a brick wall, and it happens to go fast enough, it's going to get hot enough at the front end to ignite the fuel in the engine and burn it up. So the movement is converted into heat, which then would ignite the fuel. So movement, as a rule, can convert. That's kinetic energy. Kinetic energy is converted into heat in the final analysis. Well, what could power the sun? The answer immediately was movement. Movement was what? Aha! A long time ago, they knew, because they thought, that the way that the sun got to be where it is, hot and bothered, was because the interstellar space contained lots of gas. And they figured that gravity, because we knew about Newton, we figured that gravity would pull this stuff in interstellar space together into a ball, and the ball would settle into a sun, and at the same time leave behind a slew of planets. This is all thought of in the 17th century, 18th century, that the sun was formed by gravitational contraction of gases. And if you say, that's where it comes from. The gas is moving towards the center where the sun would eventually be, would heat up the sun, make it hot, and create a hot thing that we are all benefiting from. That's the sun. That's how it happened. And thanks to the back of envelopes, you can figure out, because you can. This is high school physics. Okay, you figure out how much stuff is here. Okay, because how much is the sun? You figure out how big is the sun? It's got this amount of mass. Okay, put that much mass at infinity, and then figure out how much energy it takes for gas that far out to drop to the surface of the sun, and you find out it falls this far, and ends up at this speed, and this speed turns into that amount of energy, which then turns into that amount of heat, which turns into that amount of temperature, and you got a boiling sun. Not a problem. Very good thinking. Problem is, the back of the envelope shows that if you do that, you come up with the age of the sun. The sun could only burn for 20 million years. And while that is okay if you happen to, be a person who believes in the ages of the Bible, turns out by that time they had geology. And geology knew that things were at least half a billion years old. They knew the Earth was older than that. So the Earth was older than the sun, and that meant that the back of the envelope showed that there was something wrong with their calculation. And the thing that was wrong with the calculation was the energy from the sun doesn't come from movement, it comes from thermonuclear reactions, things that are moving. Now, no, in truth, there is movement involved, because if you have this thing called the Coulomb force. Now, the Coulomb force is the proper name for the thing that keeps your hair standing on end when you rub your body with a cloth or some discharge, and you see, your hair standing on end. That's all the protons repelling each other, so that they don't want to be anywhere near each other, because plus pushes against plus and makes things go away from one another. And so if you try to get two protons to come together and get close, they insist that they don't want to get together, because they really don't. And it's a very strong force. It's 40 times stronger, 10 to the 40th times stronger than the force of gravity. In other words, gravity is nothing, Coulomb force, everything. That's what holds our body together, Coulomb force. Okay, the Earth doesn't take us apart. The Coulomb force keeps us together. But if you try to get but there's protons and there's electrons, so they cancel each other out in our body. So it's really not a big deal. It just keeps the atoms together. The protons want to hit each other. They can't, because they're being repelled. So what can get them to get close enough to stick is speed, motion. The motion at high temperatures in the center of the sun, they can hit each other. And once they get close to touching each other, there's a force that's even stronger than the Coulomb force. And scientists, being the creative people that they are, realize that there's something stronger than the Coulomb force. And so they called it the strong force. And that's the official name, the strong force. So when the two protons get close enough together, they can merge, because the strong force says, come together, my friend, and pulls it together, and then you get the thermonuclear reaction. The two protons come together, they stick, and energy is released in the process. You get a helium, and we're on our way to making nuclear physics. So that's how the sun works. And that's all I really want to talk about in terms of the sun. I mean, we could spend weeks on the sun, but I don't want to, because we're doing the universe. And so the sun is just a thing that will help us understand the universe. Okay. So the next thing is to get an idea of how big the sun is. Okay, so now I'm going to move. So now I'm going to move this to here. Okay, so in the conversation about the size of the universe, you need to know about other stars. Other stars are not like our stars. Some are different. This gives you a sense of what other stars are like, besides our sun. So we start out, how big are the objects floating in our universe, and how big can they get, is this video. that one?
Muy bien.
Yes.
Well, I read another article. There's more than one universe.
There's always more than one universe. I'm a believer in more than one universe, but it is a matter of belief. It's either that or God. Choose your sides. You like the more than one universe. I like the more than one universe. If you like one universe, like Howard, when then Howard is a God-fearing man, he likes one universe because he says, and rightly so, that if you only have one universe, then you can't explain how nicely this one is made. So clearly, you have to have, yeah.
I believe in both.
You believe in both.
Multiple universes and God.
Okay,
Not
that
strongly, but you could twist my arm. and
one
I-
of the things about human
Change.
beings is the ability to believe completely opposite things. This is really true. We can do it. It's in our nature. Why not? Right. Yes.
If you think there's more than one universe, how would you know where one ends and another starts?
Okay. Well, that's a completely fair question, and to which I have asked the question and not received an answer. I haven't asked it of a person who's an expert, like Brian Greene. He would be the person to ask at this point. So I'm going to answer it in two ways that maybe neither of are true. Have you ever heard of an infinity of infinities? No. Okay. How many? Let's say that you decide that you're going to count all the integers. How many are there? An infinite number. Thank you very much. Yes, infinite number of integers. Right. Okay. And then between every integer and the next, how many irrational numbers are there between 1 and 2?
It's an irrational.
Any number that begins, let's say, at one point in everything you want to invent after that. Any number you want. Real. The word is real. I think that's the proper word. Real number. A real number is 1 point, say, any number of digits that continue on forever.
You could say
Like
that's
pi.
infinite.
Like pi is a real number, but there are lots of numbers that don't correspond to anything as nice as pi. So there's an infinite number of numbers between 1 and 2. Okay, so I said that there's an infinite number of integers, and yet between every integer there's an infinite number of real numbers. Okay, that's an infinity of infinities. Okay, so and you if you want to argue, no, that's just one infinity. But if that is not a good enough answer for you, there are mathematical answers in which the infinity we always talk about is Aleph null, and then there's Aleph prime, and there's Aleph 2 and Aleph 3, and they're essentially higher orders of infinity. So that's one way of looking at it. I don't like so that still doesn't say, but you have a feeling that space can accommodate only one infinity. It seems to me only one infinity. But since space is being created in the Big Bang, space is being created in the Big Bang. So space is being created, right? So I know this doesn't sound good, but imagine next door, there's another set of space being created, and they're both infinite. Doesn't seem good, but that's as far as I go. Where are these multiple universes? Infinite. If they're finite, I have no problem. You can just have them pop up like a bubble wrap, and that's what usually the analogy is: bubble wrap universe. When they talk about multiple universes, so that's fine, but they're not infinite. Then you can have an infinite number of finite universes. That's fine, easy. Just infinite number of infinite universes bothers me a little bit, just a teeny bit. I don't know how to answer it. But there are books that go there. I read them. I just forget what they said. Brian Greene. Brian Greene is the guy to look at. Okay, so did that. Okay, so why did I do that? Okay, so the reason I did that is because we go back to this guy Aristarchus, and he figured out that how far the sun was away from us. He did some triangulation. He got it very badly wrong. He got 5 million miles. Good for him. He got a great number. Other people in later ages got better numbers. People kept getting better numbers until today we got really, down to the centimeter kind of numbers. But when you knew that it was far away, and then you made one more hypothesis, you said, perhaps those little dots in the sky are stars. So now, without scientific instruments, you go, well, exactly how dim is it? And it's really hard to without instruments to judge how dim something is. But you can if you make the assumption that they're all the same size as our sun, then the brighter ones are closer, the dimmer ones are further away, and suddenly you see the universe in 3 dimensions. And you do that, and did that, he did it in BC, a couple of hundred years BC. He knew the universe was it wasn't the crystal sphere kind of thing with the stars painted on the crystal sphere. He knew it had depth and whatever. So he, aside from the fact that he didn't have any instruments, he did make one fallacious assumption, and that is stars are not the same size. Okay? You just learned that, in case you didn't know it. Yes?
No, we knew it.
Well, not everybody knows it. I mean, not everybody even knows that a star is a star. Not everybody knows that the sun is a star. It's not obvious. So now you're out there now you're now in the 20th century, and now you want to figure out how far away these stars are, but you want to get it right. So how do you do that? Because the stars are different sizes. Yes.
You judge by the movement of one vis-a-vis the other, and the parallax kind of thing.
Parallax kind of thing is exactly the right answer. Give that lady a prize. Absolutely. That is the answer. The discussion of parallax will follow. So here is parallax. Well, the parallax you can look at this picture for parallax. It shows the sun, okay, and this is the Earth, and this is the Earth on the other side of the sun 6 months later. Okay, so the Earth moves around the sun, and it's looking at something in the sky. In this particular case, the Pleiades, which is a cluster of stars that is visible to the eye. You see it many, many times a day because the Subaru emblem on the Subaru car, the word Subaru in Japanese is Pleiades, I believe. The diagram on the front of the Subaru is the Pleiades. You see 6 stars. There's really 7 if you look a little bit more carefully with the naked eye. And so if you stare at that, if you look through a telescope, there are thousands of stars there. Thousands of stars. It's really one of the great things to do. You look at the Pleiades, you can find it in the sky, train your telescope, and you see hundreds. You get a better telescope, you see thousands of stars. So when the Earth goes around the sun, you look at the Pleiades, you see the Pleiades move in the sky against the background stars. Here, it's here against the background stars. Here, it's here against the background stars. You know the diameter of the Earth's orbit because you got that right from this early in this century. And now with better instruments, you can figure out the distance to the Pleiades. It's triangulation. It's perfect. Perfect. You know the distance to the Pleiades. The Pleiades is going to help you find out about the rest of the universe. Because, well, let's continue, and let's continue with I'm going to skip the rest of the universe right now and go on to parallax, because I have a couple of videos that are just stunning when it comes to parallax. So this one shows you parallax. You see the stars? See, they're moving. Now these motions are exaggerated. This is as the Earth moves around the sun, these nearby stars are moving. You can see it looking carefully. This is exaggerated probably 1 million times. The movements of these stars are so small that you cannot see them except with the most precise and large astronomical instruments. But you can see the constellations and how they're moving, essentially exaggerated in space. So this is what they see. Now the next thing you're going to see is something far scarier. Now they're simply moving and they're not coming back. The reason they're not coming back is the stars themselves have a mind of their own, have a trajectory of their own, and they are going places. And the fact is that they're doing it so slowly we can't see it. But nevertheless, they're going places. So the Big Dipper is not going to remain the Big Dipper. It's going to change and disappear from our skies as a recognizable constellation in tens of thousands of years, or maybe thousands of years. Yes?
The Greeks must have had a fabulous imagination. Sagittarius, my sign, the Archer. I mean, I look at the stars, I do not see the Archer, I don't see Pisces, I don't see Scorpions and so forth. But they saw all of those creatures in the night sky, which is remarkable.
I don't know how mysterious they were. I do think it's interesting, but I think they had a reason to know that, because if you're out and you see the sky every night, and nobody's invented electricity to turn on a light bulb, at night it's out. You can tell a lot about the season you're living in by recognizing the stars in the sky when they rise and when they set. So you have a very good reason for wanting to label these things as constellations and such.
And ships at sea also.
And ships at sea. And you will look at Sagittarius and look to the right and take a reading there. You know, there's reasons having to do with civilization, had nothing to do with people's imagination. I'm sure that imagination played a part of it, and people, but I'm not sure they actually thought, or to what extent they thought, that those things were real. You know, another video. So this one shows the movement of the sun. See, the sun is, you just saw all those stars moving. Well, we're a star. Don't we move? Of course we do. Right? How do we move? Well,
Reluctantly.
reluctantly. Did you say reluctantly?
Yes.
I don't believe so. Okay.
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day.
Let us go away to look at our solar system from outside the galaxy.
Okay, so that's the plane of the
Then we will
galaxy.
see the full truth in the movement of the sun and all the planets revolving around it.
Look at that. Our sun has a mind of its own. Look at that.
The Sun swims in its orbit with all the planets, in an average speed of 220 kilometers per second. This is equivalent to 800,000 kilometers per second.
It's going up and down, above and below the plane of the galaxy. That's what happens with our sun. It gets up high, gets pulled down low, dips below,
However,
pulls
with
back,
all
gets
this
pulled back
terrible
up.
speed, the Sun completes one cycle around the orbit every 226 million years. Since the birth of the Sun, which means since 4.6 billion years ago, it has completed 18 cycles around the center of the galaxy.
So, that gives you some sense of perspective, and that's what I'm going to leave it now. It gives you some sense of perspective about how far the sun is in its, how far from the center of the galaxy it is. It goes around, do they say 11, what's the age of the sun? No, the 18, so this is the 18th birthday of the sun. If you count one trip around the galaxy as 1 day in the life of the sun is at its 18th birthday, the 18th trip around the center of the galaxy.
It's transit. It isn't around the galaxy because the galaxy is exceeding the orbital gyrations of the sun. It's far this way, far that way, far above, far below. So it's only a certain part of the galaxy.
It travels around the galaxy in more or less a circle, which of course is the more or less means not at all, but nevertheless it does travel around the galaxy, and the sun is well behaved, so we think it's been traveling around more or less in a circle for 18 trips around. There's more stuff further out. There's more stuff further in, and indeed the sun is orbiting the center of the galaxy where the dark matter resides. So the dark matter is in fact keeping our sun in the orbit of the galaxy. The galaxy itself doesn't have enough undark matter to keep us there from flying off into space. So it's thank you dark matter. Even though we don't know what it is, we know where it is, sort of in the center.
Huh.
Yes?
Is this at all related to gravity?
Well, in terms of this, all is because of gravity. Gravity is...
That keeps them each in their own cycle?
Right. Gravity of the matter is keeping the sun in orbit, but unlike what keeps us in orbit around the sun is the mass of the sun and the gravity of the sun. What's keeping us in orbit around the center of the Milky Way is the mass of the stars and gases that reside in the galaxy, plus much more dark matter that we can't see that's keeping us in the orbit. So dark matter has an effect not at the scale of our solar system, but has an effect at the scale of our sun orbiting around the galaxy. And that's it. Yes?
I don't know where you think it's a dark matter. We would probably be fine outside of the galaxy.
Yeah. If
And if the sun comes along.
if the dark matter suddenly disappeared in a sudden sort of way, we would suddenly start flying out of the galaxy. Now, of course, the suddenly part would take us millions of years, but instead of going around the galaxy, somebody millions of years from now would notice that the dark matter had disappeared and we seem to have veered off course. But, if the sun disappeared, or the gravity of the sun disappeared, we'd notice that we were going in the wrong direction pretty soon. But if the dark matter in the middle of the Milky Way disappeared, it'd take us a couple million years to figure it out, because it takes us 225 million years to make one revolution. So somebody would notice we're not headed in the right direction. Can we fix that? Anyway, I got to go, and sorry about that. But the lecture that the reason for this whole class being at a particular time, as weird as it is so I can get to this lecture that I'm going to now, which I don't go to often because I decide to serve you.
What's this topic?
What?
What is his topic?
Well, the topic, it's Neil deGrasse Tyson, which is why I'm really going.
Oh.
But, and he's talking to a group of maybe 20 people. And although I think there's going to be more, and so I'm trying to get there early. And his topic is how the military-industrial complex services astronomy, and astronomy services them, vice versa.
Oh.
So there.
That's a Columbia? Oh,
No.
That's the planetarium.
That's the planetarium.